Hello everyone. In this session, we learn about sequence models in neural networks. First, let us go through the index. We'll have a look at the limitations of feed-forward neural networks and convolution neural networks. Then we'll introduce recurrent neural networks. Then we'll understand the use cases of RNNs and then the limitations of RNNs. So we'll conclude with the limitations of RNNs and then we'll have a look at overcoming the limitations of RNNs using long short-term memory units or LSTMs. And finally, we'll have a look at one variant of LSTM, which is GRUs or Gated Recurrent Units. So let's start with understanding the limitations of feed-forward neural networks and convolution neural networks. In feed-forward neural networks and convolution neural networks, they have fixed length input and output. This means that the number of inputs you must have is fixed, as well as the output size. CNNs also have fixed length input and output. This is because finally in convolution neural networks as well, you have a linear layer at the end. So most of the architectures of convolution neural networks have a feed forward layer at the end which limits the input dimensions as well as the output dimensions. Even if you, let's say, do not have a fully convolution neural network, still if you provide it an input length which the model has not seen in its training period, then your convolution neural network won't be able to perform well. Also, although they have architecture which focuses on local temporal information, like the convolution neural networks, it focuses on the local temporal information. Incorporating long-term dependency inside the model greatly increases the computation and memory requirements. So if you want to increase the receptive field of a convolution neural network, you have to keep on increasing the number of layers, and that can increase the computational and memory requirements drastically. Also, convolution neural networks were made to condition local temporal information and extract features from the local information. Whereas in sequence models, let's say you want to condition or extract features from a long distance temporal locations. So this would not be possible with convolution neural networks. Feed forward neural networks can do that. They can extract features depending upon any temporal location, but they have a lot of more conditions. They can generate features from very complicated conditions, hence being stuck in a local minima, which is also not desirable. So these are the problems of feed forward neural networks and convolution neural networks. So let's introduce recurrent neural networks, which were proposed to take care of the limitations of neural networks, feed-forward neural networks, and convolution neural networks. So in recurrent neural networks, this is the simplest architecture which can explain an RNN. In an RNN, we have a sequence of inputs which we denote by xt, and then we have a sequence of outputs named ht. On every step, we have a cell state as the output, which is fed back into the neural network at every time step. You can think of A as a single hidden layer which has two outputs. F- So first, it has HT as the output and the CT as the output, and also it has two inputs, namely XT and CT minus 1. So it takes in two inputs, CT minus 1 and XT, and gives two outputs, HT and CT. And this keeps on going on for as many number of input sequences as they are in the data. Let's understand recurrent neural networks by unrolling them. A recurrent neural network can be thought of as applying the same operation by using the same weights again and again on all the inputs. So let's say we have a sequence x0, x1, x2 and till xt. Then we start with x0 and we feed a 0 vector as the cell state. From this hidden layer, we get two outputs. First is the H0 and the cell state 0. Then we feed the cell state 0 into X1 into A by providing X1 as well, and we get the outputs H1 and the cell state C1. And we keep on doing this for as many number of input steps as there are in our current data sample. So what are the advantages of using a network like this? First of all, it does not matter that T should be fixed. T can be variable and it will depend upon our data sample. Plus, in every sequence, let's say we start from x0 and x1, our cell state can contain the information of the past inputs and then extract using the information. The A matrix can extract the corresponding output and modify the cell state. So recurrent neural networks can model arbitrary length data and they can hence be used to model sequence outputs. So this takes care of the limitations of convolution neural networks as well as feed forward neural networks, that they have fixed length inputs and fixed length outputs. Recurrent neural network can have variable length inputs as well as variable length outputs. Also, your A matrix, it can be a single hidden layer or it can have a multi-layer neural network architecture as well. Also, you keep on repeating the same weights again and again. So your network size, even though it's small, it can take care of it acts as a very large neural network. So these are the advantages of recurrent neural networks and they are used in sequence models. So let's have have a look at the use cases of RNNs. Wherever we have a sequence data and we also want to have a sequence output, we'll be using RNNs. So let's say we want to predict the next word based on a sentence. As a sentence can comprise of different length of words, we can use RNNs to predict the next word. Hence, RNNs can be used to generate word-to-vec representations as well. Next, let's say we have a stock market data. A stock market data is sequential because it has the time component. So we can use the T-1, T-2, and so on samples to predict the price of a stock at the time T. We can use this to buy and sell on the stock market. Next, let's say we have a text classification challenge. In text classification, we are usually given a sentence and we have to categorize the sentence into some fixed length of classes. So we have variable length input, but the output length is fixed. So we can use RNNs in those use cases as well. Similarly, in video classification, videos also have a temporal dimension. So there are images which are three-dimensional, and then we have the temporal dimension, the fourth dimension. So we can use RNNs for video classification as well. There are many other use cases, like we can use RNNs for generating captions from an image, or as well as visual question answering challenges, in which we are given an image, we are provided a question, and looking at the image, the model has to give an answer. So the answer can be variable length, the input question is variable length. So RNNs are useful in those cases as well. So we can see that recurrent neural networks have a lot of interesting applications. But as with all good things, RNNs also have some limitations. So let's have a look at the limitations of RNNs. RNNs work good for short-term dependencies. Let's say you have x0, x1, x2, x3, x4 as the sequence. If you want to predict the output of h3, which depends upon x0, x1, x2, and x3, then h3 will be able to, your recurrent neural network will be able to get a good result on h3. So for example, if you are trying to predict the last word in the sentence, the clouds are in the sky, we don't need any further context. Let's say we want to predict sky. So if you only see the clouds are in the, it's easy to say that the next word will be sky. So your recurrent neural network will also perform quite good on these kinds of data, where your sky depends upon the words which are very close to the sky. But let's say we have a very long paragraph where in the beginning it was written, I grew up in France. Then there is a lot of data, let's say 2 or 3 paragraphs, and then we have the sentence, I speak fluent, and we want to predict which language does the subject speak. It is very hard for a recurrent neural network to demonstrate long-term dependencies. So, depending upon the country, France, it's easy to say that which language the subject will be fluent in. But recurrent neural networks are not able to model long-term dependencies, and hence it will fail if you try to predict on very long samples of data. So these are the limitations of recurrent neural networks. They arise from vanishing gradient problems, as well as there are some inherent architectural limitations of recurrent neural networks, which do not allow it to retain information for long sequences. So these are the limitations of RNNs, yet they are useful in many cases, and usually RNNs can easily model around 20 time steps. So if you have 20 inputs and you want to predict the 21st, RNNs are good for that. So now that we know about the limitations of RNNs, let's have a look at long short-term memories or LSTMs, which were proposed to solve the limitations of recurrent neural networks. So first of all, we had a representation for RNNs. This is how RNNs were looked when we unfolded it or unrolled it. You can think of RNNs in the same way in this diagram. So we have xt as the input. We have the input from the previous cell state. Then we apply a linear layer with an activation of tanh, and then we have our output. So we have the ht as the output as well as the cell state for the next cell. So this is how, so these two representations are the same. Now let's start building our intuition about long short term memory. So this is how a long short term memory cell looks like. So first of all, before we get confused by what exactly this is, first let us try to understand the notations. After understanding the notations, I'll tell you the motivation of long short term memory, what we want to achieve, and then we'll try to understand each component of this LSTM step by step. So the first thing which you need to understand is that the yellow blocks correspond to a neural network layer. So these yellow blocks correspond to a linear layer, after which we apply the sigma activation. So depending upon the activation function, the text inside the yellow box changes. So this means sigma activation function. This means tanh activation function. Next, we have the point-wise operation or the element-wise operation. So in this, if we see an element-wise multiplication, then we are multiplying these two vectors element-wise over here. Over here, we are doing an element-wise addition in these two vectors, and so on. Next, this vector transfer, it just points to where the input is coming from and where we are feeding it to the next layer. So the arrows point out the direction of the flow of the data. When two lines merge, they mean concatenation. So over here, um, you can see that the cell state and xt are merged together. So it means they are concatenated together, and then the sigma linear function is applied. Similarly, when we split one line into two lines, we say that we are copying the data. So over here, there is a junction which splits into two lines, and we copy the same data in these two lines. So this is for understanding the flow of data and the different operations. So now that we are familiar with these notations, let us try to understand what exactly long short term memory was made for. So the very first thing which RNNs fail to do is model long-term dependencies. When you're trying to model long-term dependencies, you require two things. You need to capture some data which might be required in the future and store that inside the cell state. But you want to keep on forgetting unuseful or useless information which were present in the paragraphs in the beginning. So you have to remember some things and you have to forget some things. So we need to incorporate into our architecture a way in which the model itself can learn how to forget the data which is not required and how to remember and carry on the data which is important. So that is what LSTMs are meant to solve. So let us understand how they achieve it step by step. So first of all, let's have a look at the conveyor belt. So you can think of this cell state, the way the cell state is passed from CT-1 to CT, you can think of this as a conveyor belt. In this conveyor belt, we have two operations. The first operation is a pointwise multiplication. The second operation is the pointwise addition. When you're trying to do a pointwise multiplication and the input lies between the range 0 to 1, you can think of this multiplication operation as forget operation. As your inputs lie between the range 0 to 1, you can think that either the value is very small, close to 0, or the value is very large, close to 1. If you do a pointwise multiplication, all the values where the input is 0 will make the cell state also 0. So you are losing information. While if the value is 1, then it will retain the information. So this model will predict what it wants to retain in the cell states. So the multiplication pointwise operation corresponds to the forget gate. Then after we forget the useless informations in the cell state, we want to add new information to the cell state depending upon our current input xt. So to add information to the cell state, we use the add operation where the neural networks it predicts some values and we add that to our cell state. So after the forget gate and the add information gate, finally we have a new cell state which is passed on as an input to the next cell. So this is how our cell state is modified in the LSTM. And this is how LSTMs learn to forget some parts of the cell state and to remember and add new information to parts of the other states. Next, let us try to understand how exactly the output is generated based upon the cell state, the input, and the previous outputs. So first of all, we have ht-1, which is the output of the cell at the t-1 time step. We take that and we take the input as well and we concatenate them over here. Concatenation means that we join these two vectors and we treat them as one vectors. Now, after concatenation, we apply a linear layer with a sigmoid activation to generate the features for the forget gate. So this is how we generate the features from the previous output and the current data, and we decide what we want to forget and what we want to retain in the cell state. The mathematical equation for this is that we do sigmoid activation on wf dot concatenation of the ht-1 and xt, and then we add the bias for this layer. So this is how we generate the features for the forget and retain gate. For adding information to the cell state, we use a concept named self-attention. In this concept, we use the output of the previous layer, which is ht-1. We use the current input xt, and we apply two different activation functions and two different linear layers to these inputs. So in the first linear layer, we apply the sigmoid activation function and we get it. The mathematical equation is sigma of W1 into concatenation of the previous output and the current sequence plus B, and also we get another representation by using another linear layer and the tanh activation function using the same inputs ht-1 and xt. So this is the mathematical representation tanh of wc dot concatenation of ht-1 and xt plus the bias factors, and then we get ct. Now we multiply it and ct and use that to add to the cell state. What this means is that over here we are using self-attention. This kind of architecture where we first apply a sigmoid activation function and then a tanh and then we multiply it is called self-attention, because we are attending. So using the CT we are generating some output, and using sigma we are deciding on which parts of the CT output should we focus on. This kind of architecture is not necessary. We can just apply tanh and the model can learn to generate the zero output in the corresponding locations where it finds that it's better to not uh, propagate the information. But usually the models are not able to do so. Hence, when we use sigma and tanh, the models are able to easily retain information which should have been passed with tanh and remove some information as well. So this a concept is called self-attention, and we use that to add information to the cell state depending upon the previous output and the current input. So by using the FT, we remove the information. By using the dot product of IT and CT, we get we add more information to the current cell state, and this information is passed on to the next cell state. Next comes that how do we use the cell state, the current sequence xt and the previous outputs to generate the current output. So the current output ht, it depends upon the previous cell state which has been modified and the previous output as well as the current input to the LSTM. It depends by the following equation. We first take the cell state which has been modified and then we apply the tanh function. We take that and we dot product it with another sigmoid layer gives the output depending upon the previous cell output and xt. So we concatenate them, we pass them to the sigma layer, we get OT, which we take element wise product with the cell state which has been passed through tanh. So we take HT. So this is another example of a self-attention mechanism where we are using the previous cell state. We are trying to just use the ht-1 and xt for finding out which information should be retained, and then we are so doing a element wise multiplication to preserve the information and taking that as the output as well as providing it as an input to the next cell state. So this ht acts as a similar role as the ht1 minus 1 for the next cell state. So this is how long short term memory works. We modify the cell state by forgetting some information and adding some information, and then we use the modified cell state to generate the current outputs. So LSTMs can remember a lot of information which is relevant compared to the RNNs, and they can hence model long-term dependencies in the data. LSTMs also have some limitations. They cannot model infinitely long sequences, but they can model sequences which are a lot larger than RNNs. So LSTMs are the solution when you want to model long-term dependencies. After the LSTMs were proposed, there were many variants of LSTMs which also worked quite well in modeling long-term dependencies. One of these variants, namely the gated recurrent unit, became very popular and is used extensively. So we'll have a look at the GRU, or the gated recurrent unit, and understand how it works as well. The gated recurrent unit has the following cell state. So it's very similar to our LSTMs, but it actually does not have any cell state. It combines the functionality of the cell state and the previous output. So in your gated recurrent units, this is the way in which the information is used to predict the current output. Let's go through it in a similar fashion as we try to understand the LSTMs. First of all, we have HT-1 and XT. HT-1 is the output of the previous cell state and XT is the current input in the sequence. We use HT-1 and we concatenate it with XT. Using this concatenated features, we apply a sigma layer, and we use that to remove and preserve some of the information from HT-1. So this will remove the some irrelevant information from HT-1 depending upon HT-1 and XT. And we use this in the vector in which the irrelevant information has been removed, and we concatenate it with XT over here. We'll have a look at the information of what these features are used for later on. But now let's have a look at the following branch. In the following branch, we use HT-1 and XT and apply the sigma. If we apply a linear layer and apply the sigmoid activation function as well, we do a 1 minus of the output, which just flips our output. Our output lies in the range 0 to 1. So if we subtract 1, so we subtract our output from 1 and we multiply it, then we are doing the same operation, which is the forget operation of the LSTMs. When our layers are subtracted by 1, so we do 1 minus the output of our layer, it just means that our layers are now actually predicting where the information. So when our model predicts a value of 1, it means that the model wants to forget the values of the previous features which are passed through HT-1. And 0 means that the model will preserve the values of HT-1. This is in contrast opposite to the way in which we use the element-wise product in the LSTMs. In LSTMs, we did not have the operation 1 minus. So directly, if the model predicted a value 0, then the corresponding elements of HT-1 were forgotten. But that does not matter, because anyway, the model can either predict 0 or 1, and it does not matter for the model, whatever be the value it has to predict. The main difference comes is that we are using the same output for forgetting and using the same output for remembering as well. So we remember that from HT-1, we removed the irrelevant information, then we combined it with XT, and then we passed it over here. We applied the linear layer and we applied the tanh activation function over here. So we have extracted some features from the irrelevant information removed HT-1 and XT, and then we are further removing the data which we are going to forget some information from here, and we are trying to retain that information which has been modified at this position. So whatever position we are forgetting, we are trying to remember at that position what new information should be added, and then we are finally adding it to our current output. So what this does is we forget some information at the same place where we modify and add new information. This is the advantage of gated recurrent units. In LSTMs, you can remove and add arbitrarily into the cell state. But in GRUs, wherever you forget, you add new information at that exact location again. So GRUs also work good. It does not mean that LSTMs, which were introduced earlier, do not perform well. They perform well in some scenarios, whereas in other scenarios, gated recurrent units perform better. So depending upon your use case, you can experiment with both of these units, and whichever works better is what you take. These are the mathematical equations corresponding to the operations I have talked about. You can go through each of these steps one by one to understand what exactly is happening and how exactly the output ht is predicted by using the input ht-1 and xt.